Good morning, ladies and gentlemen, in chemistry at Menominee Falls High School. We are looking at Dalton's law today. It's the most difficult of the gas laws, which is why we're not using Tyler DeWitt to explain it to you. Try to be a little bit more clear and as we go through the relationship. So it is the relationship between the number of particles and pressure. The key is volume and temperature have to remain the same. So one of the things that we gave you to do was this little simulation on PhET. I'm going to use that simulation to describe Dalton's law with you, and the first thing that you should have seen, that as you increase the number of particles, and it didn't matter if they were heavy or light, as you increase the number of particles, the pressure should increase. So that is a direct relationship. And we've done formulas that have direct relationships enough time now. You did it with Avogadro's law, you did it with Charles' law, you did it with Gay-Lussac's law. These couple of things about the formula. Does not matter what the pressure is, as long as the two pressure units are the same. If P1 was millimeters of mercury, P2 has to be millimeters of mercury. If P1 is ATM, P2 has to be ATM. Does not matter what the pressure is. N is the number of moles. That's how we count things in chemistry. We count by the number of moles. So if you're given grams, convert it to moles. If you're given liters, convert it to moles. Make sure that N is always in the number of moles. So if I wanted to use that same little simulation that you guys were using, here it is. Really super easy for me to show you. Number of particles, you can see what the pressure is. If the particles increase, the pressure is going up. If the particles decrease, the pressure is going down. Another way that we can talk about Dalton's law is something called Dalton's law of partial pressures. Dalton's law of partial pressures is not difficult, but typically when we have a gas in a container, it's not alone. Typically when you have a gas, it might be a combination of gases. You might have oxygen and carbon dioxide and hydrogen all together in the same container. So keep this as simple as it has to be. Don't make chemistry more difficult than it needs to be. Whatever the total pressure is, you just simply add up the pressures of the individual particles. So for example, on the sheet that you guys did, that's what we're kind of having you get at right here in these boxes that were in the middle. If you look at the pressure by the heavy particles and the pressure by the light particles, if you add these two together, you should get what was here. Now this isn't perfect because the pressure bounced around and stuff in your little simulation, but if you look at this chart now, you might kind of get the idea here that whatever you had here and whatever you had here should be equal to the combination of the two. And whatever you had here and here should be equal to the combination of the two. So if I wanted to show that to you in a little bit of a different example, just something that I put together, here is Dalton's law of partial pressure. P total is equal to P1 plus P2 plus P3. It could be P4, P5, P6, however many gases you have. Here are two containers. If the pressure in the first container is 300 millimeters of mercury, and the pressure in the second container is 500 millimeters of mercury, when you put those two together, it has to be 800 millimeters of mercury. That's the only way that those work out to be like that. Here's another example of doing Dalton's law of partial pressure. I made some examples over here. Again, don't make chemistry harder than it needs to be. Keep it simple. If I gave you some 3 gases in a container, just simply add the 3 gases together, and that's where your total pressure comes from. So, what happens if you get a problem when you're looking at the problem if they told you the total pressure and only one of the gases, and what they ask you for is, hey, what's the pressure of the helium? Well, it's the same idea. These two things right here added together have to be the total pressure. So if I take the total pressure and I subtract the oxygen, whatever I get left over would have to be what the helium is. This is particularly useful, this kind of logic right here, if we're collecting gas in a chemistry lab. Typically, when you collect the gas in a lab, you use a technique that's called collecting gas over water. We have done this in chemistry. You took a hose and you put it through a tub of water, and you had a test tube upside down, and you were catching some bubbles in the test tube. Here's the deal. Whatever you're trying to catch, like for example in this case, let's say that the gas that's coming out of this tube is hydrogen gas. So if the gas that's coming out of the tube is hydrogen gas and that's what you're trying to collect, so hydrogen gas would look like that because it's a diatom. This is going to be what you're catching, the bubbles that are in there, but you're collecting it over water. So unfortunately, hydrogen gas is not going to be the only thing that's in there. Since you're collecting it over water, the other thing that's going to be in there is some water vapor. So whenever you collect hydrogen gas, or any gas, doesn't have to be hydrogen gas, any gas over water, you're always going to have a little bit of water vapor that evaporates. How much? Well, that's going to depend on whatever the temperature of the room is. So one of these partial pressure problems might look like this. Let's say that you're collecting a gas and you happen to know that the pressure total is 760 millimeters of mercury. I'm not going to get into how we know that right now, but let's just say that that's what the pressure total is. This is the gas I'm trying to collect, and this is the pressure I got from water. We use that technique so often of collecting gas over water that we've actually put together a handy-dandy little chart that tells you if you know the temperature in the room, if the room's 10 degrees, this is the pressure from water. If the room's 17 degrees, this is the pressure from water. In this case, since I'm telling you that it's 30 millimeters of mercury, the room temperature must have been 29. Now that's really, really, really hot. I'm just using that to make the math easy because if I know the total pressure and the pressure from water, I should be able to figure out what the pressure from my hydrogen is. It's going to have to be 730. So those are just some ways that these partial pressure problems could look like. There is one more way that a partial pressure problem could look like, and that is if we do something called mole fractions. Mole fractions are just kind of another way of thinking about Dalton's law of partial pressure. It's easiest to explain the mole fractions by going back to this simulation that you did, and not necessarily do it in a way that we had you guys work on this one. So for example, right now when there's 100 particles in there, the pressure seems to be between 11.5 and 12. What if I make 50 of them heavy and 50 of them light? Well, you'll notice that the pressure is going to be right between 11.5 and 12 again. So how much of the pressure is caused by the blue particles and how much of the pressure is caused by the red particles? Well, because they're 50-50, half of the pressure is caused by blue and half of the pressure is caused by red. What if the particle split were something like 40-60? Again, it's 100 particles. The pressure is going to be right between 11.5 and 12. 40% of the pressure is going to be caused by the blue particles, and 60% of the pressure is going to be caused by the red particles. Well, what if it was split the other way? What if this is 70, and what if the other one is 30? And obviously I'm choosing numbers that add up to 100 really nice. Our pressure is going to be right where we had it before as soon as I let it even out a little bit between 11.5 and 12, pretty consistently between those two numbers. In this case, 70% of the pressure is being caused by the blue particles and 30% is being caused by the white particles. Now, like I said, the two numbers added up to 100 because that allows me to do my percents quite easily, but that's really what we're talking about. We're talking about when you're doing mole fractions that you're going to end up in some way, shape, or form taking some percent composition of the gas times the total. Now, I kind of like saying it like this, and that's the way I'm going to show it to you as a formula. But right now, for notes, you should probably pause this video and make sure that you have this information down for notes. Because there's, the relationship for number of particles and pressure. There's this formula that we use that talks about Dalton's law of partial pressures, where we just simply add the gases together. And then there's this last way, which we talk about mole fractions. So let me show you one example of a mole fraction problem. If you have not paused the video to write this information down, you should probably do that somewhere, because you will need all three of these in order to do some problems with Dalton's law. Here is an example of using mole fractions to solve a problem. So this is a pretty standard problem. You're told how many moles are helium, how many moles are neon, and how many moles are argon. You're told the total pressure in the container is some value, whatever that is. How much pressure is caused by each individual gas? So the first thing that I would do in this is I would figure out what the total number of particles is. Remember, we count particles in chemistry by converting to moles. So if this is given to you in grams, you'd have to convert to moles to get this number. If this one was given to you in particles, you would have to do information that we've learned in the past to get to moles, because the first thing you need to do, you have to know the total number of moles. Once you know the total number of moles, I'm just going to figure out, all right, what is the percent of helium? Take what you're interested in, divide it by the total, gives you a percent. Moles and moles would cancel out, so this is the percent of helium. What's the percent of neon? Take the amount of neon, that's what we're interested in, divided by the total. This is the percent of particles that come from neon. What's the percent of argon? Take what you're interested in, divide by the total. This is the percent that comes from argon. Now that I know those, I can kind of apply this little formula. Take the percent times the pressure total. If I want to know what the pressure of helium is, I'm going to take the percent of helium times the pressure total. This is my percent of helium. This was the pressure total from the problem. And I get this. Just for the record, up here in the problem when I was working this is 4 significant digits. This is only 3, which is why when I rounded my answer over here, I only have 3 significant digits. If I want to know the pressure caused by neon, I take the percent of neon times the pressure total. Just for the record, in my problem, I have 3 significant digits for neon, 4 for my total, which is why I rounded to only 3 in my final answer. And the last one here, if I want to know what the percent is argon, I'm going to take the percent of particles that are argon times the pressure total, and this is the pressure caused by argon. Now here's the thing. If I take this, plus this, and plus this, it better be whatever the pressure total is. If I'm checking my work, it's a great way to check your work at the end. If you add up these 3 numbers and you do not get the pressure total, something's not right with the calculation.